Hello there, Mr. Sutton here, bringing you the AB Calculus 6-9 Extra Practice Number 4 solutions on accumulation problems. On this one, the rate at which sand is poured into a bag is modeled by this R function, and we want to know how many milliliters of sand are accumulating in the bag between times 0 and 2. Well, if I have the rate at which sand accumulates, to find out how much actually accumulated, the change in amount of sand, that's just going to be the integral from 0 to 2 of r of t dt, which is going to be 15t minus 2t squared dt. All right, since I don't have a calculator for this one, I'm going to have to do this the old-fashioned way with the FTC. So this first exponent here is going to bump up to a 2. Dividing by that, I've got 15 over 2 t squared. So taking my antiderivative here, this next exponent bumps up to a 3. So that's going to be negative 2/3 then, t cubed, evaluated from 0 to 2. So I've got all of this with 2 plugged in, minus all of this with 0 plugged in. So these terms with 0 are just going to go away. Over here now we have, let's see here, 4 divided by 2 is going to be 2 times 15 is 30. And here we've got, this is going to be, let's see, 8 times 2/3, so that's minus 16/3. Well, this is really 90/3 minus 16/3. That's 74/3, which gives us answer choice C. On this one, we have a traffic engineer developing the function R, shown above here, to model the rate at which vehicles are passing an intersection over some 8-hour period. Basic idea, we want to know how many vehicles actually do pass this intersection from time 0 to time 8. Where t is just the number of hours since 6 a.m. All right, well, if I have the rate at which cars are going given here, and I want to know how many actually go, I just need to integrate that rate. So I have the integral from 0 to 8 of r of t dt. And the only way to actually find this is to find the area under the curve of r on this graph. So I've got a few shapes that I'm going to add together here. The first shape from 0 to 2 is a rectangle with a base of 2 and a height of 1,800. So we're multiplying those. And then the next thing I've got here, it looks like a trapezoid from 2 to 4. So I have a base of 1,800 plus a base of 2,400 divided by 2 times a height of 2. Next, another trapezoid. We've got a base of 2,400 plus a base of 1,400 divided by 2 times a height of 2. And then finally a rectangle from 6 to 8. So base of 2, height of 2,400, or actually 1,400. And now adding all this stuff together, let's just simplify it a little bit first. So this is 3,600. 2's cancel on this next one, so that's going to be 4,200. 2's cancel again for this next one, so that's 3,800. And then this is going to be 2,800. So let's see here. If we add all this together, well, 42 and 38, that's going to give us 8,000. Plus another 3,600 is going to be 11,600. Plus another 2,800. That's going to be, let's see, 13,600 plus 800. 14,400 altogether. So that's how many vehicles are passing that intersection, and that is choice C. For this free response calculator-based problem, we have a cylindrical can, radius of 10 millimeters, measuring rainfall in Stormville. Sounds like a great place to live. Can is initially empty, and then we have rain coming in the can from over the course of a 60-day period. And the height of rain in the can is modeled by the S function, whose derivative here they're giving us, S prime of t equals this trig function. So first task, according to the model, what is the height of the water in the can at the end of the 60-day period? Well, if I have the rate at which the height of the water is changing, to find the actual height in the can, given that we're starting with an empty can, that's going to be 0 plus the integral of S prime from 0 to 60. So that's going to be, let's see, 0 to 60 integral of S prime. Now, since we've spelled this out, we can just do the rest of this on the calculator since we already know what S prime is. So here I am on the calculator in the y equals. y1 is where I'm storing my S prime, And just quitting out of there, let me do math 9. That gives me my integral. We got 0 to 60. And we're going to do alpha trace y1 and dx. Press enter. That comes out to 171.813. And let's see here. That's going to be milliliters, or millimeters rather. So there it is. On this part of the problem, we want to know the average rate of change of the height of the water over the 60-day period. So if we knew the original height function of the water, we could just do s of 60 minus s of 0 over 60 minus 0. But since we actually have the instantaneous rate of change, a faster way to do this problem is just to use the average value kind of setup on this derivative. So I'm going to do 1 over the interval length, 1 over 60 minus 0, times the integral from 0 to 60 of the thing that we're trying to average, which is the rate of change of the water. So I'm going to put s prime of t dt in here. And now I can just do this on the calculator. So now that I think about it, recall in part A that we already found the integral of s prime from 0 to 60. So all we actually have to do on this problem that's different from part A is divide that by 60. So let's just go ahead and take our answer and divide that by 60. Let's try that again. Divided by 60. And press enter. And that comes out to about 2.864. And since this is an average rate of change for the height, this is going to be in millimeters per day. For this part, we want to know if there's no evaporation occurring, at what rate is the volume of the water in the can, changing it times 7. So this is a related rates problem. We're asking about the rate of change of volume of water, and we already know a little bit about the rate of change of the height. So for this one, we need to set up a formula that ties everything together. And surprisingly, they didn't give it to us on this one, but that formula is going to be the volume of a cylinder. That's going to be volume equals pi r squared times the height. Now we can get a little bit more specific on this problem since the can has a radius of 10 millimeters, and that's not going to change. That's always going to be 10. So we can actually just rewrite this as pi times 10 squared h, or 100 pi h. So now I have to take the derivative of both sides of this equation with respect to time, so differentiating implicitly. Derivative of velocity, of volume, is going to be dv over dt. And over on the right side, we've got 100 pi times dh over dt. So we have an inner function here. Everything is an inner function of time. And now if I want to know the rate of change of volume at time 7, well, the only place I have to plug anything in here is this dh over dt. Now, we actually have a formula for dh over dt. Since this is the rate of change of the height of the can, or the water in the can, with respect to time, that's actually what s prime is giving us. So dh over dt and s prime are the same. So really, we're just doing 100 pi times s prime of specifically 7 on this problem. And that's something we can just do on the calculator. So here's what that looks like on my calculator. I've got 100 pi times, and I already stored s prime as y1. So this is just y1. I did alpha trace y1, opened the parentheses, and put a 7 in there. So that's going to give us 602.218. So that's the number. Now, they said indicate units of measure, so what are those going to be? Well, volume, that's going to be millimeters cubed. Time is measured in days here, so this is cubic millimeters per day. For the last part of this free response problem, during the same 60-day period, the rain on Monsoon Mountain, another great location, accumulates in a can identical to the one in Stormville. The height of that water is modeled by this m function here. So note that this is the actual height, not the rate of change of the height like they gave us for Stormville. So this is a nice little polynomial. Now, what they want us to tell them, they said that let d equal basically m prime minus s prime. They want us to apply the intermediate value theorem to this function they just defined. on the interval from 0 to 60 to show there exists some time on the interval where the heights of the water are changing at the same rate. So just thinking about what's going on here, if the heights are changing at the same rate, that means that m prime and s prime have the same value, which means that if I subtract one from the other, I ought to get a value of 0. So I'm basically trying to use the IVT to show that d of t equals 0 for some c value on the interval from 0 to 60. Well, in order to use the intermediate value theorem in general, I need to have continuity on the interval. So let me just take a look at the functions involved here. We have s prime, which is definitely continuous. It's a sine function. How about m prime? Well, m prime is just a polynomial, so that's going to be continuous as well, but we only have m so far. Let's actually take a look at what m prime looks like. I'm going to need to enter it in my calculator anyway. So to take this derivative, it's actually not so bad. You don't even need to distribute this 1 over 400, because if you did that and then use the power rule, it's really the same outcome as if you use the power rule and then distribute the 1 over 400 afterwards. The order in which we multiply things doesn't really matter. So I'm just going to keep that 1 over 400 outside. And inside I have 9t squared minus 60t plus 330. So I'll just leave that undistributed. I am going to have to figure out, though, what m prime minus s prime is for various values. So I'm going to enter that on my calculator in just a moment. Before I do that, though, let me just establish I have continuity for the IVT. So since m prime and s prime are both continuous individually, that means that d of t, which is just the difference of those, will also be continuous. Now that we've established that, we need to figure out d of 0 and d of 60 and show that the value we're looking for, 0, is between those two results. So let me go to the calculator for this. Here I am back in my y equals. Now recall that I already had s prime as my y1. Here's the m prime I just came up with. I've entered that as my y2. And I'm not actually going to use y2 directly because really what I need is m prime minus s prime. So I'm going to go to y3 here, and I'm just going to do alpha trace y2 because we want m prime minus alpha trace y1. So that's m prime minus s prime. Quitting out of there now, I need to figure out d of 0 and d of 60. For d of 0, we do alpha trace and then pull up y3 and plug 0 into that. And since I've defined what m prime is, and I already knew what s prime was, I can just plug things into d without showing any other work now. So let's see here. D of 0 comes out to exactly negative 0.675. And let's find d of 60 now. I'm just going to yank my input from before, so I have a y3. I'll just use 60 instead of 0. And then pressing enter for that, that's approximately 69.377. Now the value we're looking for, namely 0, is between these two values that we just came up with. So therefore, since we have continuity, and we're going from this value to this value, and zeros between those, it follows that we have to pass through 0 on the way. So by the IVT then, there is a time on the interval from 0 to 60 for which the heights of our cans are changing at the same rate. For this calculator-based free response problem, a store is tracking the sales of one of its popular board games over a 12-week period, and the rate at which games are being sold is modeled by the differentiable function g. G of t is measured in games per week, and we've got some table values for g of t. Great. We want to know, for part A, the value, approximately the value of g prime of 8, using the data in the table. So they didn't tell us the value of g prime of 8, because this table is g, not g prime. And we don't know what the g function looks like exactly, so it's not like we can just take the derivative and plug 8 in. But if you're trying to approximate an instantaneous rate of change, and you have this table data, you can use the average rate of change of g over an interval that includes 8. So the interval from 6 to 10 would work nicely. That's the closest interval involving 8. So I'm just going to do AROC from 6 to 10 of the g function, and that'll help me approximate this g prime. So I've got g of 10 minus g of 6 over 10 minus 6. So specifically, notice I said that g prime of 8 was approximately equal to this. I know it's not exactly equal, and I'm doing some truth in advertising here to get full credit. So g of 10 was 2100, g of 6 was 900. You could actually leave it like this if you wanted and just stick units on the end, or you can simplify it. This is really 1200 over 4, which is going to be 300. And since we've got games per week over weeks, that's going to be games per week squared for our units. On this part of the problem, they want us to approximate the integral from 0 to 12 of g of t using a right-Riemann sum, and then explain what it means. So approximating this integral, I'm going to write that this integral is approximately equal to, and notice I put approximately here, otherwise I don't get full credit, because I'm showing people I know this is not really the true value. So right-Riemann sum, that means we're going to be adding a bunch of rectangles together, 4 specifically, using the data in the table. So each of these is going to be a base times height type of area. For the first rectangle that goes from 0 to 3, I have a base of 3, and the height I'm going to be using, I have a choice between a left height and a right height. Since this is a right-Riemann sum, I always use the right height. The right height is the right one to use. So we have a base of 3 times a height of 450. Next, we have a base of 3 times a height of 900. And you always have to look at the bases here, the intervals. We have a base of 4 to get from 6 to 10 on this next one, times the height of 2100. And then we have a base of 2 times a height of 2400. You don't have to simplify this, but I'm going to anyway, so let me see what that comes out to. So I'm going to plug all that into my calculator. Mama didn't raise no fool. Let me see what it all comes out to. That's 17,250. And since I'm basically in this integral multiplying games per week by weeks, dt has units of weeks, the weeks cancel out and we just end up with games for the final unit there. Now let's talk about what we just found. Since this was the rate of change of games sold, integrating that from 0 to 12 gives us the total number of games sold in units of, well, games from week 0 to week 12. For this part of the problem, we have one salesperson who believes that starting with 2,400 games per week at time 12, the rate at which games will be sold is going to increase at a constant rate of 100 games per week per week. Well, I would like to believe that too. That sounds like it would be very good for business. Based on this model, we want to know how many total games will be sold in the 8 weeks from time 12 to time 20. So the general question here, how many games are we selling, that's going to be an integral that we need to use on the interval from 12 to 20. But what are we integrating? We have to come up with basically a g function to integrate on this interval. So to come up with the g function, well, what have they given me so far? They actually haven't given me g. They've given me g prime, the rate at which g, which is the rate of change, the rate at which g itself is changing. So we're starting with g prime of t equals 100. I'm going to use a little diff-EQ here to come up with a formula now for g of t. And I can do this because they told me that I have 2,400 games as my value of g at time 12. So I can use this initial condition with a little diff-EQ dance on this in order to figure out an actual function for g of t. Once I have a function for g of t, I can then integrate it from 12 to 20. So, diff-EQ time. Taking the antiderivative of both sides here, I've got, let's see here, just g of t on the left side. That's the antiderivative of g prime. And I have 100t plus c on the right side. Now to find the value of this mystery constant c, I have to plug in my initial condition. So I know that at time 12, so 100 times 12 over here, we have a g of t value of 2,400. So I can write 2,400 equals 100 times 12 plus c. Well, 100 times 12, that's really just 1,200. 2,400 minus that is also 1,200. So that's our c value. So then I can write g of t equals 100t plus 1200. Now this only works between times, well, for times after 12 weeks anyway. So I couldn't really use this for anything before 12 weeks, but I'm just using it after 12 weeks because I just want the integral now of g of t from 12 to 20. So let me write integral. Games sold is going to be integral from 12 to 20 of g of t dt. And I could do this pretty quickly without a calculator, but I'm going to use one because I have it available, and I mean, hey, why not? So I'm going to enter my g of t function that I just came up with in my y equals under y1. Quitting out of there, let me do math 9 integral from 12 to 20 of, and then let me do alpha trace y1 and do a dx. Let the calculator do the heavy lifting here. And in that period, we're selling 22,400 games. For the last part on this problem, another salesperson believes the best model for the rate at which games will be sold in those 8 weeks between times 12 and 20 is this m of t function, which is this crazy-looking exponential quadratic hybrid sort of thing. And this is a function that gives us games per week. So based on this model, we want to know how many total games to the nearest whole number will be sold during this period. So this is fairly straightforward. You've got the rate at which games are changing, and again, this only applies between weeks 12 and 20. So we're just going to integrate this rate of change over the interval from 12 to 20. So integral from 12 to 20 of m of t dt. And let's just plug this in the calculator, because they already told us what m is, so we can just integrate it without showing any further work. So for my first step, to make things a little bit more seamless, I've entered m of t as my y2 and my y equals. Quitting out of there, we've got math 9 for integral. I'm going to go from 12 to 20, just like I did before. And this time I'm going to do alpha trace y2, because that's where I have m of t. Do a little dx there, press enter, and nearest whole number now, so that's 15,784 games sold in that time period.